Assalamu alaikum wa rahmatullahi wa barakatuhu. So in this video, in the previous video, we have seen the auto transformer and their usage in the power system. Now let's look at the three-phase transformers. So we know that almost all the major power generation and distribution systems in the world today are three-phase AC systems. So transformers for these three-phase circuits can be constructed in one of the two ways. One approach is simply to take three single-phase transformers and connect them in a three-phase bank. So another alternative approach is to make a three-phase transformer consisting of three sets of windings wrapped on a common core. And so both designs are in use today. So a single three-phase transformer is lighter, smaller, cheaper, and slightly more efficient because we have three different transformers, and any disturbance in one phase can be replaced by another single-phase transformer. So three separate single-phase transformer has the advantage that each unit in the bank could be replaced individually in the event of trouble or the fault. A utility would be only need to stock a single spare single-phase transformer to back up all three phases, potentially saving money. So here in this way we can have three single-phase transformers which can be connected in either ways. So that connections we will be look just now, and or we can have the say one transformer with three windings on the core. So there are four ways in which we can connect the windings. So you might have seen the words Y and delta connections of the windings, or delta or Y connections. So now we can connect the three-phase transformer banks in different ways because we have the primary side voltage and the secondary side voltage, secondary side winding and primary side winding. So we can connect the three windings in the form of Y, Y, or Y delta, delta Y, or the delta delta. So the key to analyzing any three-phase transformer bank is to look at single transformer in the bank. Any single transformer in the bank behaves exactly like the single-phase transformer. So the impedance, voltage regulation, efficiency, and similar calculations for three-phase transformers are done on a per-phase basis using exactly the same techniques already developed for the single-phase transformer. So we obviously the purpose of this statement is that we will not going to calculate all these parameters and again and again for the three-phase transformer, because we can do the same for the three-phase transformer on a per phase basis. So what we will then look the effect of these different windings. What happens if we are making the windings as YY? What happens to the system Y delta and their benefits and drawbacks, and delta Y and delta delta? So let's look at them one by one. So here case 1, three-phase transformer connected as YY connection. So we can see that these are three windings, and this is NP1, NP2, NP3 for the primary side, number of turns in primary side, three phase. So they are connected in the Y connections. So in the Y connections we have to connect one winding, one side of the winding of all the three phases as a common point, while we take the other sides of the winding as the output of one A, B, and C. So the voltage from phase to phase is written as V line phase, and the voltage of one phase is V phase on primary. Similarly, we can do the same connections for the secondary side. One side of the winding is connected to make a neutral point, and then we have this V phase, and then we have line to line voltage. It could be from A bar to C bar, B bar to C bar, B bar to A bar, whatever it is. Obviously the dot conventions are there to show that the current is entering here is positive, and the current entering here is positive, and the current leaving is positive. So these are just the connections of the three-phase transformer in YY connection. So the primary voltage on each phase of the transformer is given as V phase primary is VLP square root of 3, that we know from our previous circuits analysis subject analysis from the circuit analysis subject. So the primary phase voltage is related to the secondary voltage by a trans ratio of the transformer. So here it is related with the trans ratio A. So the phase voltage on the secondary is then related to the line voltage on the secondary. V line phase is equal to square root of 3 V phase. Overall, the voltage ratio of the transformer is then V line voltage by V line secondary side, V line primary side divided by V line secondary side. And these are square root of 3 V phase primary over square root of 3 V phase secondary. So they are same, so that will be simply A. So for YY, the transformation ratio is just simply A, line for primary to secondary windings turns ratio. So the YY connection has two very serious problems. One, if the loads on the transformer circuit are unbalanced, then the voltages on the phases of the transformer can become severely unbalanced. So in this YY connection, normally we have to keep the voltages very balanced. So obviously sometimes it's not possible. So mostly we don't use this YY connection. So the third harmonic voltages can be large. Harmonics, you have studied in the signal systems that if we have any signal that can be represented as the sum of the sine waves of infinite series of sine waves, which is called the Fourier series. And the Fourier series actually tells us that how many harmonics and their amplitudes are existing in the any signal. So we are looking at here the third harmonic voltage. If we have the system of 50 hertz, the third harmonic frequency will be 150 hertz, and if it is a 60 hertz system, so third harmonic frequency will be 180. So that will be just simply multiples of 60. So fundamental is 60 or 50, so then the third harmonic will be accordingly. If it is 60, the third harmonic will be multiple of that 60, that is 180, and if it is 50 fundamental frequency, then the third harmonic will be 150 hertz. So here we will have the third harmonic voltage that will be very large. So if a three-phase set of voltage is applied to a YY transformer, the voltages in any phase will be 120 degree apart from the voltages in any other phase. However, the third harmonic components of each of the three phases will be in phase with each other. So that will create a huge voltage at the frequency, which is I told you that that will multiple of the fundamental. Third multiple of the fundamental means that if it is 50 hertz, so it will be 150 hertz, that we will be having a very large voltage at 150 hertz. Since there are 3 cycles in the third harmonic for each cycle of the fundamental frequency, there are always some third harmonic components in a transformer because of the non-linearity of the core, and these components add up. The result is a very large third harmonic component of a voltage on top of a 50 or 60 hertz fundamental voltage. So this third harmonic voltage can be larger than the fundamental voltage itself. So both the unbalanced problem and the third harmonic problem can be solved using one of the two techniques. The first is that solidly ground the neutrals of the transformers, especially the primary windings neutral. This connection permits the additive third harmonic components to cause a current flow in the neutral instead of building up large voltages. So that will be drained out from the transformer. So the neutral also provides a return path for any current imbalances in the load. Or we can do another, add a third tertiary winding connected in delta to the transformer bank itself. If a third delta connected winding is added to the transformer, then the third harmonic components of voltage in the delta will add up, causing a circulating current flow within the winding. So we can see that the winding are connected in the form of delta, so they will be actually causing a circular currents in this delta winding. So this suppresses the third harmonic components of voltage in the same manner as grounding the transformer neutrals. So the delta connected tertiary winding need not even be brought out of the transformer case, means we can leave it there inside and it will be just dissipating that current. We just have to cool it down. But they often are used to supply lights and auxiliary power within the substation where it is located. So, or we can use it for certain purposes. The tertiary windings must be large enough to handle the circulating currents, so they are usually made about one third the power rating of the two main windings. One or the other of these connection techniques must be correction techniques must be used anytime a Y-Y transformer is installed. In practice, very few Y-Y transformers are used since the same jobs can be done by one of the other types of the three-phase transformers. Now, let's look at the case 2 that the three-phase transformer are connected in Y delta connection, means primary side is Y connected and the secondary side is delta connected. So here line primary voltage is square root of 3 phase voltage, but in the delta connection the line voltage and the phase voltages are same, line to line, and the phase voltages are same. So in this case, V line primary by V line secondary is equal to square root of 3 V phase primary over V phase secondary. So that square root of 3 factor will be multiplied with the transformer turns ratio A. So here we will get the square root of 3 times A. So we will have this transformation ratio which is higher than the actual transformation which higher than the which we have seen in the Y-Y connection. So these are just the connections of the three-phase transformer on the primary side, and these are the delta connections on the secondary side. So Y delta connection has no problem with third harmonic components because we already have the delta connected in it, since they are consumed in a circulating current on the side delta. This connection is also more stable with respect to unbalanced loads, since the delta partially redistributes any imbalance that occurs. But this arrangement has one problem. Because of the connection, the secondary voltage is shifted 30 degree relative to the primary voltage of the transformer. So there will be a voltage shift between primary and secondary voltage. So that the fact that the phase shift has occurred can cause problems in paralleling the secondary of the two transformer banks together. Paralleling means that if we have connected one transformer, so and if we want to bring another transformer live on the system, so we have to be very careful because of this phase shift. So the phase angles of transformer secondary must be equal if they are to be parallel, which means that attention must be paid to the direction of the 30-degree phase, means primary is ahead of the secondary voltage or secondary voltage is ahead of the primary voltage. So we have to take care of this transformer bank to be paralleled together. So case 3 is almost similar to the case 2 because just the transformer winding is now delta Y and the delta is connected there, and the same problem of 30-degree voltage between primary and secondary occurs. And the case 4 is the delta delta connections. In the delta connection, we have no phase shift associated with it and no problems with the unbalanced loads or harmonics occur. So here the transformation ratio is again A. So there is no constant multiplied with this transformation ratio. So that will be VLP over VLS, which is equal to V phase voltage over V phase secondary voltage, that is A. So this is for the delta connection. So I hope you have understood the connections of three-phase transformers and the problems and their solutions associated with their connections, whether they are connected as YY, Y delta, delta Y, or delta delta. Still, if you have any questions, you are feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuhu.